Yes. Yeah. وعليكم السلام ورحمة الله. Okay. بسم الله الرحمن الرحيم. الصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. Great to see you all. Many new faces. So how many are you are still new? KFUPM first semester? 1, 2, 3, 4, 5. Okay, so this is probably your first class, right? Okay, so I hope you're not disappointed. I hope you don't get disappointed at the end. Okay, so I hope you'll all enjoy this course. So I would like first to introduce myself. So my name is Rami Rashad. So I'm an assistant professor at the CIE department. And I'm an engineer by training. So I'm a mechatronics engineer. So I had my bachelor's and master's at the German University in Cairo in Egypt. And then I worked there for a while as a teaching assistant. And then I went to the Netherlands to do my PhD. I had my PhD at the beginning of 2021. And then after that, I worked there for 3 years as a postdoc. And now, since last year, I'm here at KFUPM. This is the second time I'm giving this course. For those of you who are new here, you can still choose, to either keep the course or drop it. Okay, so you can try it for a couple of weeks and then you can choose to drop it. You don't need to wait that long. Okay, also for those of you that have been here before. So in the last time I've given the course, it's all recorded. All of the materials are available online. If you cannot access it, just send me an email. I'll send you the quick link. So you can, make up your mind very quickly. You don't need to wait for a couple of weeks and then lose all of that time. Okay, it's very easy to see from the beginning. It's what you expect or not. Today I'll just, try to promote that course for you, and we're not going to spend so much time. It's like I'll tell you the truth of it. It's a very hard course. Okay, it's very mathematical. I'll try to scare you off. Once you run away, we're going to be left. Only the interested people will remain. And that's how I like it. Okay, so if you feel it's not yours, just run away as quickly as possible. Okay, so I'm open about it. But before scaring you, I'll also try. Maybe you'll like it. Maybe. So I'll try to convince you. But a little bit about my research here at KFUPM. So I'm heading the autonomous robotics manipulation group as part of the Smart Mobility and Logistics Center. So we're doing their research related to drones, but not any kind of drones, the drones that are able to interact physically with the environment. So this is the kind of research we're doing. At the essence of what we do is geometric methods. And today we're going to get a glimpse of what we mean by geometric methods. And the whole course is about geometric methods. Okay, so the course is actually about the official name of it on the registrar is actually Special Topics in Intelligent Automation and Robotics. But so this is, just for you to get to know the nature of this course. This is like a placeholder course that we have in our department. You can always use it, to change it and, to try out different new courses. Okay, so this is why I'm giving it as part of that course. We're just trying it out. Okay, this is why this version of the course will be a refined version of what we had last year. And yeah, it's evolving into something hopefully that in the end will be a standalone course eventually. Okay. So the true name of the course, again, and the true topic of the course actually is geometric modeling and control of robotic systems. Okay, there are 3 aspects of the course. First, the geometric approach. The second one is then we're doing modeling and control, and in the end, the type of control we're doing is model-based control. So there is, if you're interested in AI and learning and model-free control, okay, all of that stuff doesn't exist here. It's all model-based control. We write equations, then we try to use this for control. So in the end, actually, our controllers are equations, okay? And our physical system, no matter how complicated it looks like, this robotic system is in the end equations. So the whole course is mathematics, okay? This is why it's heavily mathematical in that respect. The kind of robotic systems that we deal with here are 2 types: multi-rotor aerial vehicles, so drones that fly using propellers, okay? And you can have not just the standard quad rotor that has, 4 propellers pointing upwards. You can also have, weird configurations that you might be interested to have them in certain applications. So this type of, these drones is what you're going to be learning how to model them and how to control them in the course. And then we're going to also focus on fixed base manipulators. So fixed base manipulators are just multiple rigid bodies connected to each other through joints, and then you have a fixed base. So just what you call a robot arm in the end, or industrial robots. Another topic that's very relevant to what we do in research, but we're not going to be covering in the course at all. Okay, is floating base manipulators. So floating base manipulators is what you see here in these pictures when you have a robot arm on something that's moving. Okay, this moving can be another robot that's moving on the ground, a robot that's going undersea, a robot that's flying in the air, and this type of systems is at the frontier of what people are trying to do in robotics nowadays, and unfortunately, we don't have much time to go into them properly. But the basis that you learn here to do for how to model and how to control multi-rotor air vehicles and fixed base manipulators will help you out if you're interested in doing this kind of research. Okay. If you watch the previous year's videos, I was very ambitious. I hoped we actually can include the floating base stuff into the course, but I was okay. These two were already too much for the students. Okay, so. But if you're interested, we can always talk about them, later on, as extra material. Not through the semester, you'll be already completely occupied with this course and others. But maybe later on, if you're interested, we can gather, a group of interest people and we can discuss about them. We have here a celebrity in the room. Okay, so and this is, the first person I actually learned from him this geometric stuff. So Stefano Stramigioli is not a student here. Okay, you might have guessed. Okay, so Stefano Stramigioli is actually the head of the robotics and mechatronics department at the University of Twente, where I had my PhD. He's my PhD advisor. He's technically my academic father. Okay, so and he'll be joining us here at the KFUPM for this week. Okay, so he'll be giving multiple seminars. Okay, I think you already got the invitation for some of them. One is tomorrow, one is Tuesday, and another one is on Wednesday. Okay, I urge you all to go and get your mind blown with some cool stuff. Okay.
We're very fortunate to have Rami as a teacher.
So.
I can say
it depends on their grade, Okay. So why the geometric approach? Okay. So geometric modeling and control is the word geometric comes. It actually refers to these tools. It refers to the tools of differential geometry. So differential geometry is a branch of mathematics that it focuses on, and focus on this word, it focuses on non-Euclidean spaces and coordinate invariants. Okay, most of your engineering education and most of engineering education at large actually focuses on coordinate-based Euclidean geometry. Okay, maybe maybe you're not able to decipher what that means, but you're all familiar with Rn, right? If I tell you Rn, if I tell you just take a numbers and put them over each other, and you have a vector, and you're very familiar, right? You know how to deal with them. You have linear algebra. You know how you can build matrices, and you can take determinant of matrices and trace and eigenvalues. You're very familiar with all of that stuff. If you have MATLAB and your Python programming skills, this becomes a piece of cake for you. Okay, so you're very familiar with this kind of math of algebra, and so when we say Euclidean geometry, we mean please come in. So when we say Euclidean geometry, we're talking about Euclidean space, okay, which is in the end Rn. Well, if you have just one number, this is just the real line scalars. If you have R2, which is R and R, you have two variables, like X and Y, and if you have three variables like X and Y and Z, they pop up all over the place, right? And you can usually generalize into N. If you had linear control, then you have like state space state space formulation where you have x dot is equal to ax plus bu. So your u is another vector and x is another vector, x dot is another vector, a is a matrix, b is a matrix, and you start to do control with all of that stuff. So this is the linear control. And even if you try to do nonlinear control, even if you take nonlinear control, the starting point is x dot is equal to some function of x, and x is also a vector. X is also Rn. And guess what? Okay, once you deal with real systems and real world problems and complicated systems, you figure out, okay, this math, it's too limited. You cannot do a lot with this kind of math. So this is just a point in the sea of many examples that I can tell you about where you might find this non-Euclidean spaces. For example, you go up to, we'll start with the simplest thing you can even imagine, just a pendulum. Okay, the pendulum, you just have something that's going back and forth. It's hinged by by a joint on the top, and you just have gravity, and it just keeps on going forever. If you don't have any friction, if you have friction, it just swings, and then after that it just damps out. The configuration space of this very simple mechanical system is not Euclidean. Okay, you treated Euclidean by some some stuff or some we're going to be discussing. Okay, but in the essence, it's not Euclidean. Okay, then you take multiple pendulums. Okay, for example, you take multiple rigid bodies and you connect them all, and you make, for example, you put motors on them, and boom, you have just a robot, an n degree of freedom manipulator, and the configuration space is also not Euclidean. Okay, it's what's called Tn. Okay, all of this will not make sense at all at the moment. If you have a planar mobile robot, just a robot moving on the ground, the configuration space Q is also not Euclidean. Multi-rotor aerial vehicles, they're not Euclidean. If you have an aerial manipulator, this floating base manipulator, when you take, it's a very simple idea, right? Let's take a robot and put it on a drone and let's fly with it, and let's design a controller. What's the configuration space? It's also not Rn. Okay, so and more and more and more. Even if you're doing learning and you're interested in machine learning, and you have probabilities, the covariance matrix for just of a simple Gaussian is not, does not live in Rn. If you have rigid body inertia, also they don't live in Rn. So it's very hard, so it's very limited. If you only have in your toolbox only Rn stuff and linear algebra stuff, you're very limited in what you can do in real life. So differential geometry is fundamental in modern theoretical physics, and this is just we're not going to be covering that, but just to give you how things evolve. People thought for a long period of time that we live in space plus time, that we have R4, we have R3, that you can just walk in space, and then actually before that people thought that that the Earth itself was R2. That it's flat. None of you, I hope, are a flat earther. These years, okay. Otherwise, you should get out of the course.
Talking about until today, people say no, it's not like fair. It's just a flat.
Yeah, if you believe that, please get out of the class immediately. Okay. I hope you don't. Okay. So even you just have a sphere. Okay, and the sphere itself it's locally like R2, but it's not globally R2. Okay, this will make sense in a couple of lectures, inshallah. So Earth's sphere is S2. It's not flat. It's not R2. But even time itself, how is time interacting, with space? It's not like time evolves in one direction and space is the next three. It's not like we're living in R4. Actually, all of them are all of this space-time relativity. If you watch Interstellar, you understood nothing is because of you don't know geometry. Okay, if you understand a little bit of geometry, things begin to make a little sense. We're living in a manifold, essentially. This is how what modern theoretical physics is telling you about. So it's not space plus time. It's not R3 plus R1. It's actually one word. Space-time is one word. Okay, and in Arabic it's called zamakan. Okay, it's not zaman and makan. It's zamakan. It's one word. Okay, it's not a typo. It's actually one word. Okay, space-time. And we'll get to this idea of geodesics later on. So I want to tell you about, okay, so this is just why the geometric approach. So this is just a bit of motivation. You understand nothing, of course, but this is just to show you how much there's out there. Okay, if you think, okay, these kind of systems I'm interested in, and you're the kind of person that can take mathematics, stay. If you have allergy to mathematics, please leave as fast as you can. Okay, because this course is full of mathematics. So the topics that we're going to be covering in the course is, first, we're going to be, we cannot jump into the sea without, the proper tools that you need. We can spend lectures and courses just, covering differential geometry. If you're interested and you find an interesting course in the mathematics department that cover some of that stuff or some of differential geometry, you can take it and try it, okay? But we're going to be covering the basics of what we need. Okay, so this kind of stuff is available you can watch a series, and it's like 10 credit hours, if you really want to understand what differential geometry is. And I most likely after that, you're going to feel you don't understand it. So it's very heavy stuff. It's very heavy mathematics. So we're going to be covering, just a bunch of the basics that's needed. And this will be a nightmare for you. Okay, so this is actually, the first five lectures, and this is the best thing that actually makes people leave the course. Okay, because it's very scary at the beginning. So that's what I'm telling you. The course is already available online. You can just look ahead and see if this stuff scares you and you feel okay, no, that's not what you expect. You know what to do. Okay, if you like it, okay, then you're up for a ride. After that, we're going to be looking at rigid body modeling. Okay, so this is the beginning. When we shift, we leave the mathematics and we go a little bit, start to talk about physical part and rigid body mechanics and kinematics and dynamics. And then we start to use this basic principles and let's take rigid bodies and connect them together so that we can make a fixed base manipulator. So we're going to be looking at joint, how do we model joints, how we look at forward kinematics and dynamics. And if we have some time, we can look at just a little bit about actuation and gearing and how friction goes into the game. Then so up until this part, it's going to be the midterm. Okay, then we're going to have the midterm exam and the Ramadan break. And then after we come back, we're going to be shifting to control. Okay, everything after the midterm will be control. So you see that the course is very well balanced into almost half of it is modeling and the other half is control. When we go to control, I don't expect any background of you here. Okay, so you don't need to have taken any nonlinear control, any adaptive control. Nothing is needed. The only thing you need to be familiar with is linear algebra. Okay, that's the starting point. So if you're familiar with linear algebra, okay, that's the starting point. If not, you can catch up in these first weeks and you can just try to refresh your memory. If you want, I can send you some material if you just contact me. But the starting point here is talking about Lyapunov stability. This is one of the topics of nonlinear control. We're going to be covering it very, very briefly, and then we're going to be using these tools to try to look at geometric PD control. Most of the stuff we're going to be doing here in the course is just PD control. And you're going to be seeing how powerful is it, okay, that you can do with just the simple proportional plus derivative control. Okay, provided that you do it, with the geometric tools that you learn. This is the whole story. Most of the stuff we're going to be doing in the course. And I'm going to show you how this is applicable for a very large class of multi-rotor aerial vehicles. And then we're going to be finishing the course with fixed base manipulator control. We're going to be looking at motion control and we're going to be looking at interaction control. And interaction control, we're going to be seeing, that robots are made not just to move from one place to the other, but to go and interact. So there is, we need a way of describing this interaction and designing controllers so that we can make these robots interact in the way that we want, in a desired way. I'm saying it again and again. Okay, just so that if you're still hesitant, okay, I'm trying very hard to scare you off. Okay, so it's an intensive graduate level course. Okay, it's an advanced applied mathematics course, and as I mentioned, the prerequisite is only linear algebra. I don't expect you to know anything. We're going to be building all of the tools, bit by bit. Okay, sometimes it will be a little bit fast, sometimes it will be a little bit slow, but in the end, you're going to be you don't need to know anything about just study the material of the course. Okay. Another prerequisite is MATLAB, because we're going to have a lot of MATLAB assignments. If you want, you can also do it in Python, but the material provided to you will be in MATLAB. These are the two books that we're going to be mainly relying on. The yellow one is called Geometric Control of Mechanical Systems by Francesco Bullo and Andrew Luiz. The other one is Modern Robotics by Frank Park and Kevin Lynch. Most of the fixed base manipulator stuff, you're going to find it here. Most of the math stuff, in general about, instability on manifolds and geometric control, you'll find on the other book. Okay? Both of them are available as PDFs on Blackboards. Okay, so you don't need to look them up. And I think I have it later on about what the reading material will be provided with. This is the distribution of the grades of the course. You have a lot of assignments. You have 5 assignments. Each assignment is for 5%. It's distributed, throughout the course. You have at the beginning we're going to have a lot of theoretical stuff, theoretical assignment, and in the end we're going to have a lot of MATLAB assignments, programming that you need to see how visually see what these tools we're learning, how they work out. We're going to have just one quiz. Okay, it will be immediately before the midterm exam. It's actually part of the midterm exam, just like a practice for you, so that you don't go to the midterm exam and get a heart attack. Okay, and then we have the final exam as usual in the end. It will not be comprehensive. Okay, so again, so you're welcome. And the group project is another nightmare of the course. Okay, this is the place where you have full freedom to be creative. So it's up to you. We'll be providing you with some ideas and some examples, and you can take it as much as you wish. Okay, we're going to be doing stuff with simulation. Okay, it will be group project. Okay. Depending on the number, it will be either groups of 3 or 4. Okay, so start to make friends now. You're going to be looking at building a robot. Okay, so in simulation, everything will be in simulation. Okay, so you're going to be learning about the closest that you're going to be with with the theory, with the math. We're not going to be discussing any practical aspects here in the course. You're going to be doing model-based control, just to move the robot from one place to the other. But you also have the flexibility to go and test, and how do we interact? How do I simulate, for example, a valve that this robot can open? How can I simulate a surface that this robot can write on, and so on and so forth. And why I'm saying the project is a nightmare is that it has to be complex. Okay, we're going to be doing some of the easy examples. Some of the stuff that we're going to be doing are very generalizable. For example, we're going to be doing controllers for for fully activated drones that that have N propellers. It's the same controller, right? So don't in the end just choose 4 propellers and say, okay, this is my project. This will actually be just a small assignment throughout the course. So that's to be something a little bit more involved that you can work on throughout the course. And as I mentioned, it's all in simulation. Okay, but more on that later. You should only start to think about the project when I tell you. Okay, so for now, just forget about it. There is no such thing as a project until I think it's about 5th or 6th week. Okay, forget about it. Okay. As you see here, I have the video lectures. They are all recorded. All of them will be posted on YouTube, but as unlisted. Okay, so if you pass by, if you ask questions, okay, nothing will be public. Okay, you have when you're watching the videos, if you find you appeared, or your voice appeared in any moment, and you want to be deleted, you have the right to be forgotten. You just tell me I don't want to appear in the video. Please modify it. I'll do it immediately. Okay. Unless you say so, I assume everything is okay with the videos. Okay, and then at the end of the course, it will be available publicly. Okay. So you have the chance, just to review it, and if you said a bad joke and you want to remove it, if you said something political and you don't want to get arrested, all of this can be completely removed. Every week you're gonna be provided with some reading materials from the textbooks. Okay, so you have all of the textbooks available. You can start reading them now, okay, on Blackboard. But every week I'll be providing with just some reading material that are very focused on what we do, so that some people literally get lost with just skipping through pages. And I know sometimes you're overloaded with a lot of stuff. So the reading material is the minimum that you should read, okay, along with the slides, along with your own notes. It's very important. Should have your personal notes with you all the time. Okay, so most of the lectures will have all of the lectures will have slides, but many so I think the majority of the lectures will also have written notes on the board. So usually I try to have a mix every lecture of both. That we have slides at the beginning, I just tell you about the how a recap of what we did, and what some nice pictures or some nice videos, and we immediately jump into the math. The best way to learn math is just to write it bit by bit. Okay, so this is what we're going to be using the board for. We're going to be starting today with that, so we're not done yet. Okay, so be prepared. So if you don't have a paper and a pen or tablet now, start to make friends and try to ask for paper, because you'll need all of these notes. There is a work in progress, but it's not done yet. So we're hoping, me and the TAs of the course, we're hoping that we can provide you with the lecture notes, which is it's like a textbook, but it's only of the material that we cover here. Okay, so it's like very small bits, of the material that we cover, and all of the notes and all the exercises. But it's a lot of work. I cannot promise that you're going to have the lecture notes. Okay, so it's only the slides, the reading material, and your notes. Okay. So before we start, any questions? Yes.
Thank you for the introduction. You mentioned that we are going to be using very intensive mathematics.
Yes.
One of the reasons is when we go into the real world application, none of it is actually as simplified as we generally do. My question is generally when we go into even in the robotics, even in the complex robotics, we are able to simulate, we are able to understand everything, even in the simplified format of mathematics. We bring it into the natural numbers, we bring it to the vectors and matrices, even in the linear, we bring it down even to the linear systems, and we are still able to develop controllers, and we are still able to develop controllers and other things, the mechanics and everything. Why do we then need to go into the complex systems to model everything?
It's a very good question. Let me rephrase it. I think what you mean, I think what you understood from me is that when I said matrices and vectors, are bad, that you thought that we're not going to be using vectors and matrices. Is that correct?
Basically, we are going to be using. I should put to put it exactly. We are not going to be using Euclidean spaces.
Yes, right.
My question is when we can use Euclidean spaces and still we are able to get where we want to go.
Yeah.
Why do we need to go into the other aspect of?
Very good. It's a little bit ahead, but the spaces I showed you, all of these configuration spaces, they locally are Euclidean, but globally they are not Euclidean. So you always have the trick that very close. You know how you do linearizations. You know how for those of you who took nonlinear systems, how that nonlinear systems describe much more generally than linear systems. You all agree on that, right? Statement. But does that mean that linear control and linear systems are not useful? You can always do what? Linearization, exactly. You can always linearize, and then you can use linear control. But when is the linear control valid in that respect? In the very close region to where you linearized about. That's exactly the whole idea. So locally, some of these all of these spaces, they locally look like Euclidean. So you get fooled by, what? I can actually I can represent them using Euclidean. The simplest example is actually rotation matrices and rotation. You all know, are you all familiar with Euler angles? Euler angles are 3 numbers, right? So, x1, x2, and x3, they are, R3. Okay, just think about them, just 3 numbers. And you can do a lot with them, right? You can represent orientations, you can build, controllers for drones and stuff like this. They're only valid locally. That's the same idea, You can do this controller will be only valid if if you give it small disturbances. But if you try to give it large disturbances or try to do maybe flipping with the drone, it doesn't work. It's exactly the same, This is just a short answer without the details are okay, in the next 15 weeks. Okay. Any more questions? Okay. So since you're all still here, okay, and you
comments?
Yes, of course.
Rn is the curse. Because you're taught to use Rn, and the world and the universe is not Rn, because of the reason that Ryan just said. What you will learn in here, it's really understanding really what's going on. That's the core. Because then it's really the geometry is what it's all about. Engineers, especially, are always trained to use coordinates, and your brain is deformed by it. But what is behind is much more, and you will hear it.
And another thing is that I'm going to be criticizing a lot vectors and matrices, but we're going to be still using vectors and matrices. But you're going to have a new view of what they are, right? So in the end, a matrix will not be just some numbers, just stacked next to each other. They will have meaning behind, and this will become, close. This is what you get from the geometric way. So computation, you still use it looks like it's like the same tools, but they are much more advanced because you just look at the true nature of where the variable lives. Okay, just keep that, cling it, and it will make sense throughout the next weeks, inshallah. So now this is the point where we go to the board. But before that, what we're going to be covering today, and let's see. Okay, I think we still have some nice time. So in the next 45 minutes, what we're going to be doing is looking at the mathematical foundation. We're going to be starting immediately from with topic 1. Okay, we don't have any time to waste. And the first thing I'm going to tell you today a little bit about sets and set notation. So if you're familiar with this, you're going to find that there's a lot of overlap with what you already know. But this is just to set the ground especially with notation, especially of what do we mean by certain symbols? Because we're going to be instead of writing just words, we're going to be using a lot of symbols to say some statements very efficiently. But first, there's a word that you hear a lot in mathematics, which is a space, right? Have you heard this word space? Euclidean space. you have something, you're all familiar with what a set is. You're pretty sure you heard what a set before, right? But you also heard about a space, for example, a vector space, right? So this, what's the meaning of this word space? Because it appears a lot. And a space is simply just some set and extra structure that it has. Whenever we say a set, okay, if you look at this table here, the set is usually the most abstract concept that describes, okay, a collection of objects or a space without any structure. You can think about it also like this. So if I describe if I have, for example, a variable, for example, like velocity or momentum or mass matrix, okay, or inertia, okay, in general. So, and I want to describe where they live, okay. So usually I say, for example, they live in this set, and I describe what this set is and blah, blah, blah. When you talk about the set, this is the most abstract, okay, concept and doesn't have any structure, okay. And this will be clear, okay, what we mean today. And after that, if you want to do something with this set, you need to give it this structure. And sometimes you have this for granted. You say, okay, and this is the problem of Rn. So in Rn, you have a lot of these structures. So you're free to do a lot of stuff with Rn. For example, if I give you a vector of Rn, you can add two vectors to each other. You can multiply a vector by a scalar, you get another vector. You can make vectors, you can put them next to each other, you make a matrix. You can take the eigenvalues of this matrix, you can take the trace and the determinant, right? And you can do all sorts of stuff. You can do all of the decompositions that you're familiar with, and so on and so forth. But when you were working with, with these complex systems and this complex differential geometric concepts, we need to make sure that what's the difference between all of this, structures, okay? And at what level are we talking about? So you can have two sets that are very similar at the set level, but not similar at maybe at the manifold level, okay? And of course, this is all, at the moment Chinese, okay? Because you don't understand anything from what I'm saying, okay? But with time, it will, when you watch the video again and again, okay, it will be clear. And now it's time to write stuff. And this is how the lectures will be usually, okay? So we start with the slides, and then we go to the board and we just, we dive into the math stuff, okay? So this is where you should start right, okay? Even if you're gonna be getting the notes, okay, afterwards, even if you're too lazy, to write, just writing is the best way, to understand this stuff, okay? It's magic. Try it and you won't regret, okay? So the first thing we're going to be discussing is what is a set. So I mentioned, okay, a set, okay, and usually when I say a set, this is what comes into your mind, right? You imagine like we have a collection of stuff, and inside of them maybe I have, like a circle, and a triangle, and a square, and a star, and stuff like this. And I maybe have one circle and another circle and a third circle, and I have one square and another square and stuff like this. If I tell you this is a set, you all agree? And these shapes can be anything. They can be numbers, by the way. This can be 1, 2, and 3, and 4, and 5. They can be -1 and -2. They can be, the fractions. They can be anything, So in the end, I can even have a set of vectors. If you know what a vector is, I can have some vectors, the one that that you're familiar with, and so on and so forth. So a set in the end is just a collection of objects. This is the most intuitive way how you understand what the set is. But mathematically, actually, it's it's much more, delicate than this. Actually, mathematicians, they usually they have what's known as axiomatic set theory, okay? And this is they build exactly some axioms based on which a set, the definition of the set and the operations, the basic operations on the set, they just evolve from that, okay? So this is a little bit of of the edge where you as an engineer can dive in, okay? For those of you who are interested, just to get this glimpse of what all of that means, I'm going to be posting some lectures, okay, on Blackboard. These are all supplementary. You don't need to understand them, okay? If you know what this picture means, you're good to go, okay? That's it. But there's some interesting mathematics that go beyond that, okay? So this is for the highly curious people. So in the end, when I say an S, okay, set S, this is what you should understand, okay? Yes. No idea. I know. Sorry. Okay. if you pick any one of these elements, okay, let's say, for example, you call this triangle X, and you want to say that X belongs to this, set. Usually, this is the kind of notation we use. We say X belongs to this S. Okay? So this, the small epsilon, you read it as belongs to. So X belongs to S. Okay. And you can write it, by the way, both ways. So actually, you can say that X belongs to S like this, or you can write it that, for example, Y belongs to S like that. Okay? It works both ways. Okay, it's the same symbol. Okay, so don't get confused. If we have, for example, if we take all of the circles, and for example, we say that all of them, they make another set A. Okay, so we have another set A, and we want to talk about the relation between A and S. Okay, so then we have the symbol. So we say, for example, A is a subset of S. Okay, and again, the same symbol can use it both ways. So you can, for example, say another set B is a subset of S. Okay. The way how we define the set S or A or B is usually by, you can do it either two ways. The first one, you can say all of the elements that are inside of this set. So for example, you can tell me, for example, A is defined as, so this symbol is, you can read it as is defined as. Okay? If it's just if it's just an equal, you just say A equal to. Okay? But when we put these dots here, we say that A, the symbol A is defined as, and it's a set. So usually, we use this notation to define a set. It's just these curly brackets, and you can enumerate all of the elements in there. Okay. If it's a finite set, you have just a finite collection of variables, then it's very easy. But usually you have infinite number. Okay. So for example, you can say that A consists of 0 and 2 and 4 and 6, and then you use your own logic to fill in the place. What do you think will come next? 8 and so what are all of these? Even numbers, right? Even positive numbers, okay, including the 0. So another way of defining this set is usually by saying, and this is the more common way, because it's not always possible that if you have infinite numbers that you can find in a very easy way to just write it in one line. But the more common way of defining sets is by defining in this way, by saying that A is the set that includes all of the elements X that live in S. If I say like this, then A and S are what? No, if I say A is defined as the set that has all of the elements X that belong in S. Then what's the relation between S and A? They're the same. So usually you try to say, I want to reduce a little bit. I want to have some conditions. So usually you write it like this, and you say, we have some conditions on X. Okay, so this will be some conditions on X. Okay, for example, we're going to have a lot of examples later, but this is just, the abstract definition. So the way you read this statement, okay, this mathematical statement is as follows. So you say that the subset A is defined, so A as a set is defined as the subset of S that contains all of the elements X such that you satisfy these conditions. Okay? And sometimes we write these conditions explicitly. Okay, you can have more than one condition. It's not just one condition. Usually you have condition 1, and then you have comma, condition 2, comma, and so on and so forth. There is a way how you can combine different sets together. So if I give you a set A, okay, and a set B, and I tell you make a new set out of them, okay, we can define a new set, and this is its name. Okay, and we call this the Cartesian product of A and B. So this is a new set. A X B is the name of the set. Sometimes you say, okay, this is too much. I'm going to be calling this, for example, C. Okay, so I just call the Cartesian product. And how does it look like from inside? Actually, it's just it's a set that contains all of the elements A and B such that, so it's like a tuple. Okay, so this thing I wrote here is actually called the tuple, where you just take one element from the first set and then you add one element from the second set. If you have, you know, times C and times D and so on, you can, you know, just put them after each other. They are just called tuples. This is not a vector. You might say, okay, you know, I've seen this before. This is a vector. No, it's not a vector. Forget about the word vector now. This is just what we call an n, just a tuple. Okay, just an ordered set, you know, of elements. So A and B, where A is in small a is in capital A, and small b is in capital B. This is just how the set is defined. Okay. And if you, sometimes it's very helpful that you take the set A and you just make copies of it. Okay. So for example, sometimes I want to take the set A, right? And I want to multiply it by A, and then by A, and so on. All of this, I do it, for example, n times. Okay. A common notation for that is that you simply write an A, okay, and you put an n up. Okay. You might say, does this mean that we're taking every element and then we're taking like a square of it? So for example, A2 is that as a square of this? No, forget about squares, forget about multiplication. There is nothing, there are no operations. There's nothing called addition. There's nothing called subtraction. There's nothing called multiplication. It's only sets. You see, this is what I mean by abstract spaces. Just, you know, nothing, there's no operation. You can do nothing with these, okay, with these elements, with these sets. Usually this is called, okay, the n, you know, Cartesian, n-fold Cartesian product of the set A. Okay. And there's something that's familiar to you here, which is, what does this remind you of? Where do you work with this all the time? Rn. I mentioned a lot Rn, right? So what is Rn? It's simply R and R and R and R. For example, you say, for example, I have Rn is like, I call X to be a vector in Rn. You call it a vector, okay? But usually in this notation, it will be called an n-tuple. Okay, so an element here is simply an n-tuple, okay? For example, what lives here in this an is simply a1 and a2 and an, okay? Just numbers. Yes, Fahd.
Let's say that I have a set of A that has a bunch of triangles and B a bunch of squares.
Yes.
What does C look like? Both
So AR triangles. Okay.
A are squares.
So triangle square. Whenever you pick something from the set C, whenever you pick one element from the set C, you get a pair, triangle and a square.
First one, first one.
Yes, this is what this condition says, right? For example, if I tell you,
Any. No, you said first any element from one and any element from the other.
I think you're talking about the order, right? So the squares first, and then the.
A is like the first triangle is red, the second triangle is blue.
There is no first and there is no second. That's one of the things. We're talking about sets, right? A set you can think of it visually like this. It's a bag that has all of the elements inside. When I say I want to pick one of the elements, you just put your hand inside, you get something out. There's no order, there's no structure. Okay. There's no, I'm pretty sure you think about, you know what, that I have this element and the element is next to it, and I can maybe take it, I can sum them together, or I can take distance, and you know there's no structure.
Let's take one of the triangles. Is it excluded from the set?
We're not taking this exclusion. I'll mention it in a bit. Yes, you can do that, but what you're talking about is that actually I'm creating a new set that removes that one from it.
I have 5 triangles and 5 squares.
Yeah.
Does that mean I cannot take the same triangle with another?
No, you can. It lives there. It's just, you know, it's like A is, they're not. We're not. You're thinking again about structure. You're thinking about subtraction. You're thinking that I'm taking something from something. Again, all of this is structure. At this level, we have no structure at all, just elements. Yeah.
All possible geometry. All square, for each square you have all triangle, for each triangle you have all square. So it's like all possible combination. That's why it's called Cartesian product. We take all the elements from one side and all the elements on the other side.
Yeah.
Like making a new set.
Exactly. The only thing that you think about right now, that's the correct way of putting it, we're creating a new set. So the C is a new set that was different from A and B. That's it.
scenario of A playing by A.
Yeah.
This case, we're just like A is a set of triangles, and the other A is also a set of triangles.
That's right. So think of it this way. Nothing is, you're not taking from anything. It's not like you don't have any, it's not like you're thinking maybe in terms of, some data structure where I'm taking an element and then it gets reduced. There's nothing there. It's just elements, pure elements.
The only structure that the set has, sorry,
No.
The only structure, set has structure, but the only structure it has is called cardinality. It's the number of elements. That's the only thing it has. So if you have A has 5 elements and B has 10 elements, that's the only thing you can say about the set. A cross B will have 5 times 10 elements, because all possible combinations are part of the new set. So the cardinality of the Cartesian product is the multiplication of the cardinality of each of the two.
Exactly. And speaking of the cardinality, usually we denote it by this letter. So sorry, this symbol. So when I put like this I mean how many elements are inside of A. That's it. There's other ways how you can make sets out of old ones. For example, you're all familiar with the union, right? So I can give you A and B. You can take the union of them. Okay? If A had triangles and B had 3 squares, what is the union of these two? It's a new set that has 3 triangles and 3 squares. That's it. What about the intersection? It also creates a new set. Okay? It just looks at what are the elements that are here and the elements that are here. For example, if this one had like a star and this one had a star, what is the intersection of these two? Only one set that has the star. Is it 1 star or 2 stars? 1 star, exactly. So you see, there is no copy pasting. It's just what is the element that's here and the element that's there. Okay, it's the star. What if we don't have anything that's that's inside of that intersects with A and B? We introduce something called the empty set. Usually the empty set has this symbol. Okay, it's like a phi. Okay, it's not exactly the phi that you're used to when you write a Greek phi. It's actually it's another mathematic. It's another symbol of. It's just called the empty set. You're gonna find it's more like of a circle. When you look at it, in the notes or in the book, you're gonna see clear this is it's a weird phi. It's not the one that let's say a little bit curvy that you're used to. Yeah. Whenever we have A intersect with B, and it yields the empty set, and you take the union of A and B. Usually we call this the disjoint union. Okay, so for example, in this case, this is the disjoint union of A and B. Okay, so this is A, this is set A, and this is set B. This is the disjoint union of A and B. Of course, just the word disjoint, okay, it's just an extra condition that means that originally A and B had no intersection between them. Okay, so this is just an example. And of course, I'm updating these figures along the way. So actually, I should remove this one.
And in that case, you sum the cardinalities.
And so on and so on. Okay, you have to watch. That's why your notes. Don't rely only on the end and the end photos, because you need to write all of this. How it evolved. Okay. So let's see how much time I have. Okay, very nice. So now let's look at some examples. So from now on, okay, this is all of the pieces of information you need to know. Let's just look at different examples and different sets. At least things will become clearer with these examples. Yes.
So when we are subtracting the cardinalities of the sets, what is the case when we are subtracting the cardinalities of the set? Because the union, it's logically the addition.
That's right.
But when we are subtracting them,
W-
so an intersection is not subtraction.
That's right.
Section, we look at the nature of the elements.
That's right. So when you're saying subtraction, you're talking about some structure that's given to numbers. And we don't have structure. We don't have any addition, we don't have any subtraction, we don't have any multiplication. Forget about all of that. I know it's very hard. I know it's very hard to let go of all of these concepts, but just take it as boxes, sets with some elements inside. And just think about this basic structure. And then we're going to be building it step by step. Okay, at this moment.
It's on the cardinalities. What I think you mean, sorry, Rami, you don't mind,
Of course not.
It's for example, if you have two sets and you have the intersection is not zero, so you have certain things which are common, right? You can count them, right? So the number of elements which are common are always going to be, for example, less than the maximum. You can reason in that way. That's what you should think about, is the number of. Because that's the only structure that the set has. So that's the simplest structure, and two sets that have the same amount of elements are the same set, basically. Okay, because you can always have what is called the bijective relation between the two. Okay, so the cardinality is just the number of. Just think it that way, and then you will see an example that going to show you.
I think in general, any of two sets is equal. The cardinality of any of two sets is equal to the cardinality of each set minus the cardinality of the intersection.
That's correct. Absolutely.
Yes.
Absolutely. If you take that's the correct formula. In fact, the intersection, so the number, you take two sets. The number of this plus the number of this, if the intersection is zero, it's the sum. But if there is an intersection, you have to subtract. That's exactly what you said.
Yeah.
Very, very, very logical, actually.
But not because that we have something called pluses and minus. That's a completely different story. Very important. Pluses and minus will come later into what we call a vector space structure. More on that, or fields, but more on that later.
History of humankind is that you count things. That's the basic things. You start counting people, etc. So that's the concept of the set.
No. So speaking of, what you count with, okay, so usually you define, this is one of the examples, you use this symbol to define what's known as integer numbers, right? You know what integer numbers are? So -4, -3, 0, 1, 2, 3, and so on, right? Can go up to back and forth to infinity. So this is what you call by Z. What do you call by N? This is another example. It's another set. Okay. So N is the natural numbers, which are what you count with, right? So 1, 2, and 3, and 4. Do they include the 0? No. Okay. We don't include the 0. The set of real numbers, okay, R is just, usually you have a nice way of, a very compact way of writing R, You know what R is, right? Just a set of all the real numbers, but usually you write it like this, right? Have you seen this before as an interval? It's all of the numbers and everything in between that goes from minus infinity to infinity. Okay, so everything, in between. To look at this way of, defining a subset. So let's actually look at a subset of R. So let's, for example, define this set. We're going to be calling it R plus down. And now get used to this fact of, just defining symbols, Sometimes the symbol is explanatory. It tells, what does it mean. Sometimes it's actually ambiguous. It doesn't, it's not clear exactly what it means. That's why you should always say, what do you mean by that? What do you mean by R plus? It's all of the elements X that live in R, that belong to R, that satisfy a certain condition. What is that? X is greater than 0. And this R plus, okay, is simply a subset of R. You all agree? It's just a subset. Actually, any set that you write as as elements of this superset, this is always a subset of that, and this is a superset of that. So it's by definition you can always deduce that. So this is the set of positive real numbers, and you see that this symbol, by the way, is actually ambiguous. Sometimes you find it. Some authors choose to include the equality. Sometimes they mean you know, I mean x's that are non-negative. So they are 0 and all of the positive. And sometimes they mean by R plus, they are the set of positive real numbers. And you have to ask, you know, the author, what do you mean by that? So it's always go back. So this is like a first lesson. Whenever you're reading a paper, for example, don't always take the symbols for granted. You might be used that, for example, x, okay, is this direction and y is that direction, right? I might choose this is y and this is x. And I knew you were completely confused. So always go back to the notation part. And this is exactly what we're doing here in the first part of the course. We're just getting used to the notation so that later on, you know, you always, whenever you find something that's new, either go back to the previous, you know, slides, you can take it to ChatGPT, it will tell you very quickly what it is, okay? Or come ask me, okay? 3 things, okay? Start with ChatGPT, okay? And
Be critical.
yes,
Because it also makes mistakes.
you have also the Z plus. How can we define the Z plus? It depends on what do you want to include the 0 or not, okay? So let's say that we say yes, of course, yeah, it includes the 0, okay? So it includes this one and that one and so on and so forth, okay? A compact way of actually writing the Z as the sum, as the union of 2 other sets. Which 2 sets do you think would make up the Z plus? Sorry? Exactly. The n, the natural numbers, and 0. And now you see something here. Do we mean the element 0? Or do we mean the set 0? You mean the set 0, right? If this is the element 0, right? Sorry, if you mean by this notation that this is the set 0, and I want to take the element of that, so actually you should write something like this, you know? O is in O. Do you all agree? Do you all like this notation? It's a very ugly notation. That's why sometimes you have a definition of just a set of one element. And you're going to find this a lot, you know? This is just a set of one element, okay?
That notation is created a big paradox in mathematics.
Yeah. And then you have the set of rational numbers, okay? So the set of rational numbers, they are defined as, they are all the elements in R. So Q is a subset of R, such that now we're going to be introducing a new symbol that's called there exists. It's not a capital E. Actually, I exaggerated it here a little bit. It's just it's a small capital E. I don't know if that makes sense or not. Okay, so it's like a tiny capital E that's reversed. We call this there exists. So the way you read this is that the set Q is defined as the set of all elements X and R such that there exists some P that lives in the integer numbers and some Q that lives in integer numbers. And another condition is that X, you can write it as the fraction of P and Q. This is how you would define the set of rational numbers. Yes. Absolutely. Yes. So Q should not include the 0. So how can we exclude the 0 from this set here? You simply have this notation to say that I want to exclude from the Z the set 0. This is usually the standard notation. So this is a new set. You can call it anything. You know, you can call it now. You know, you start to lose. You know, you start to get out of out of the symbols to use. Okay, when you write a lot of mathematics, hopefully in your thesis, inshallah, you're going to be finding, you know, it's very hard, you know, to have a symbol for every thing I want to discuss. If you're being very precise, so sometimes it's just enough to write it like that. But how you should read that is that this whole thing is a set that's made up of Z excluding the 0 from. Okay? So if I pick anything from this set, I'm going to always get integer numbers. Okay, so I can get +1 and -1. I can +2 and -2. I can get +10 and -10, +126 and -126. But I can never get 0. Okay, so this is what the Q is. Does it make sense for everyone? So far, so good? Okay.
An interesting thing is that the number of elements that that set has, which is infinite, right? There's a lot of elements. You can see that exactly the same amount that of number that n has. It's been a very something for later. If you're interested, but was a very strange results in mathematics, because you think, how is it possible? I can show you later, but it's just a curiosity, a mathematical curiosity.
So there are a lot of stuff that that are made for YouTube. You know how people go to YouTube just to get too confused? This is part of this, videos that are there. Okay. So if you want to get confused and you want to watch some nice stuff, this is the kind of stuff you should watch. Okay. We don't need that in the course. Okay. So don't worry. Okay. It's beautiful, of course. Yes. And then you have this picture. Okay. It's just, so that you can have some visually that there is a bigger set than the R. You can actually make R. You can make two copies of R, but different from R2. And you're all familiar with the complex numbers, right? You're all familiar with complex numbers. Complex numbers actually is made up out of two sets. Again, just think of it as a set. You can have set of real numbers, and you can have the set of the imaginary numbers, right? We have to talk about what the imaginary numbers is and what's the relation between R and. But as sets, just have a couple of these. They are not intersecting at all. So there's a disjoint union. And inside of the real numbers, you have as a subset, you have the Q. And inside of the Q, you have a subset, the Z. And inside of the Z, you have the subset, the N. Okay? So N is a subset of Z. Z is a subset of Q. Q is a subset of R. And R is a subset of C. Okay? So this is at the set level. Okay. What about the complex conjugate? No such thing. What about taking two real numbers and adding them together? No such thing. Okay? Forget about all of this. No structure. No operations. We can't do anything with these numbers. Just get them out and count them, and that's it. Yeah. Okay, so 3. Now another example, which is what we're going to be calling the set S1. Okay. The set S1 is defined as follows. Is all of the elements x1 and x2 that live in R2 such that x1 squared plus x2 squared is equal to 1. This is just some condition that we need the elements, the real numbers, to satisfy. What does this remind you of? So visually, what does this look like? Unit circle, exactly. This is called the unit circle. So this is like a set of unit circle. And you can actually generalize this definition to any n. Okay, so sometimes this is called the one sphere, or just the unit circle. And visually, it's just, I'm actually having R2. So I have here x1, and I have x2, the one that you're used to. Okay, there's no relation between them. You just have 2R like that. And visually, all of the elements that belong to this line here is what? Is the set S1. Make sense? So all of the elements that live here, all of the pair of points, you see here, S, if you take one element from S, what do you get? A pair of x1 and x2. Okay. If I take another one, I come here, I get this pair. I come here, I get this pair. Is there anything wrong if I take the same point again? So for those of you who are confused about taking a point and exclude it, I'm not taking anything. I'm not cutting anything from the circle. It's the same circle. I just go and pick something. I find myself here, find myself there, I find myself here. I always get a pair of x1 and x2. If I always take this relation that x1 squared plus x2 squared is equal to 1, I always find that I always find they satisfy this condition. You can generalize this to what's known as the n sphere. Okay. So we can define the n sphere as the elements, all of the n plus 1 tuples that are in Rn plus 1, such that the sum of the squared value of all of these elements is equal to 1. So this is what you would call an n sphere. Yes. Which one? No.
Should be -1, but
So if you have an S1, it should be an element of Rn plus 1. So it should be R1 plus 1, should be an R element of R2. Okay? And what about S2? What is S2 here? So what do you think S2 is? So what would the set S2 look like? Just a unit sphere, exactly. Okay, so you have something that, it's in 3 dimension, okay? You have all of this. That's the best I can do in 3D, okay? I cannot do better than that. Yes. The sum should be n plus 1. Sorry, yeah, that's a mistake. Yes, you're correct. N plus 1. Yes, absolutely. Thanks a lot, brain. And now we're going to be getting confused a little bit between 2 things. Between what is the difference between this Sn and taking the set, right, and combining it n times, which is the Cartesian product. So in other words, what's the difference between this one and actually another Sn, for example, that we can, for example, call it S, but no, it's not, it's not bolded, it's not doubled. Actually defined, let's say that we define this as S multiplied by Sn times. Okay. What's the difference between this and that? This is called the n sphere. While this is called just the Cartesian product of S, okay, n times. No?
N is dimension for the first one.
Exactly. What's the cardinality of this one? What's the cardinality? How, if you pick an element of, is this Sn, how many numbers do you get? N. You just get n. And how many do I get here? N plus 1. You see here, if I pick an element from S1, what do I get? I get a pair of elements. I get 2 elements. But if I take an element, if I had S1 here, you're thinking about this S. How many numbers do I get? I just get 1 S. Okay. So usually if you want to write this, then I would have, as an element, I would have that something that lives here will have something that looks like this. So S1 up to Sn. While if there's something that lives here, it will actually have something that looks like x1 up to xn plus 1. They are both sets, but different sets. They have nothing to do with each other. Okay? So I'm deliberately confusing you here because if sometimes, you're just too lazy to, for example, to give different, symbols. And sometimes I can write this S and I can also write this Sn. Don't get hung up on the symbols, Every time go back and see what is this set defined. Don't say that this, this is Sn, so it should be the n product of something, of n times something. Unless it's defined like that, then it means that, okay? And you see, okay, we can have very similar symbols, okay? And they mean completely different things. They're even not the same dimension, not the same cardinality. Yes.
These 2 sets, basically, they have also different dimension as well.
That's right. Yes, absolutely. This has n elements. This has a cardinality of n. This has a cardinality of n plus 1. Absolutely. Yes.
Think about it in terms of, let's say, trying to geometrically draw it in terms of Cartesian plane. Let's say their coordinate, the dimension of their coordinates will be different as well, because the Sn, the set and sphere, has different number of coordinates that are required to draw it.
What do you mean by coordinates? Did we discuss coordinates? Did we say what the coordinates are?
their dimensions. In
The
terms of-
dimension is the cardinality. You take an element and you count how many elements inside of it.
Tricky then, be careful.
Yeah.
Because cardinality is actually infinite to all these sets. So it's a parametrical thing. So there's something going on. It will become clear later. But be careful because all these sets really properly say cardinality is infinite because the points are infinite. Okay, but the number of parameters you want to describe the set with, see it this way, and then it will come clear later.
That's the dimension. So there's actually the dimension of the set and there's the cardinality. But now we're not going there. It's like if I would take in one element from here, okay, how many elements are in this set? That's another story. Then if I pick one element from there, how many smaller elements is it made of? So this one is made from n+1 smaller elements. This one is made from n smaller elements. So what I said earlier about the cardinality, yes, yeah, sorry. So this was not correct. Yes, absolutely, you're right.
But in case of S, it's equal to the cardinality of S times N. So
That's right. Absolutely. Yes, exactly. Yes.
Sorry, guys, the cardinality of all these sets in infinite.
yes.
No, except for he's talking about this example. If S was already finite,
That is infinite n times the cardinality of that set. Because if you have a real number, you can stretch it.
no, but this S is not this is not S1. This could be something else. So this could be already a finite set.
Oh, okay.
That's right. Yeah.
That's cool. Yes.
Yes.
Very
So-
good. Yes. I made a mistake. Yes. If you consider S any set, indeed.
That's
it's
right.
n times. Yes.
And now the last thing we look at is that what if this S was actually S1 itself? What happens when I take S1 times S1 n times? Okay. Is this like Sn? Is this equivalent to Sn? So that's a question. Is this equivalent to Sn that we defined earlier? No. So it's a completely different object. Okay. So this is not equivalent to Sn. And actually this one has a name. Okay. So this one is usually given the name of the N torus, has a double T. And this special set will appear later on because this is the configuration space of an n degree of freedom manipulator. And I say, oh my God. So now you're talking about robot arm that, just moving around and it's doing welding and it's doing, opening a valve, or maybe I put it on a drone and it's flying. What does this have to do with all of this, sets? This is the first connection, see, okay? So this is very mathematical, but when you go to the real life and you look at how can I describe the configuration of one of these manipulators, you immediately fall into this set. And you need to be very careful what does it look like and stuff like this. And you see here that this is not Sn. It actually has a much different shape. We don't know what shape of a set is. We don't know how can I take differentiation of elements in that set. How can I define differential equations? We cannot talk about any of that stuff. So now we're at the set level, and that's it. Okay. So don't try to do anything with the sets because you cannot do. Just the best you can do is that you say I can have this set and that set and this set and that set.
And
that's it.
concepts, as simple as they are, as you're learning it for me, but I can tell you that a lot of professors doing robotics worldwide don't understand this, and they do it wrongly. So that's why I'm saying you are fortunate to be here.
Yeah. So that's it for today. So yes.
The T.
Sorry, yeah, the N torus. This is called the N torus. Okay, if you look it up, you're gonna find a donut shape. Okay, yeah. So that's for later. Okay, so today everyone will have attendance just as a gift. Okay, and because I'm also too lazy to count the attendance now. This should not go on tape, but okay, but that's for later. So, جزاكم الله خير.